All right, class. This is 8B problem set. This is part one. I'm expecting to have at least two parts, possibly three, depending on how long this takes me. I'm not going to go through each problem, though, because you guys are going to actually do a bunch of the problems yourselves. And then if you have questions, we can talk about them in class. And, so far, whatever. So I'd like to do, for this screen here, I'd like to do 46A for you, show you what it means by both H's are bonded to C, show you how to start a problem like this with the Lewis structure. There are a list of steps in the book. They are long, and I think I can condense that a bit. One of the things they do, though, is they do say, like, add up the number of valence electrons. So we can do that. I can show you here that I have two H's. Okay, so that's two electrons, valence electrons. I have one C that has four valence electrons, and I have one O that has six valence electrons. So that means that 2 plus 4 is 6, plus another 6 is 12 electrons I'm going to show in my Lewis structure. That's supposed to be an E. There we go. All right. So 12 electrons. Now here's what I'm going to do. I'm going to actually match them up so that they work the way I want them to work. I'm looking here for the central atom. I have two choices. Because of the two pairs I have on oxygen, I can only get two bonds out of the oxygens here. Here I got four bonds, but hydrogen only has one bond. So almost always I pick the central atom to be the one with the most bonds, like the most available bonds. The lowest electronegativity would probably be hydrogen, but hydrogen can never be a central atom because it only can produce one bond ever under any circumstance. So let's go with carbon. So carbon's going to look like this over here. I put dots around like this. I put my oxygen. Well, first of all, let's do exactly what it says. It says both hydrogens are bonded to the carbon. So we might as well bond to hydrogen like this and bond to hydrogen like that. Now, both hydrogens are bonded to the carbon. That means I have two extra bonds. Now, one of those bonds is going to go to oxygen. So my oxygen is going to look like this, and I have an extra bond like that. Anytime we have an extra, not an extra bond, an extra valence electron. Anytime we have a single valence electron, like we do over here with oxygen and we do here with carbon, then we should link them together to make more than one bond, more than like a single bond between the two elements. Now, when I do this, now here's the reason why I do this. If I take a look at, I just switched colors so I can show you. If I take a look at carbon to see if I have an octet, I have two there, two there, two there, and two there, because I just moved that up to make it look nicer. So that means I have four bonds, which is 8 electrons total. Now, if I consider and I'm going to use a different color here, for oxygen, if I consider 2 plus 2 is 4, there's 6, and there's 8. So both carbon and oxygen have an octet, and that's why I write this like this. Now let's move on to the next one. The next one, I'm skipping B and C for you guys to try and see if you can figure out how to do that. I kind of fit them together like it's a puzzle piece. This is going to be a little bit different, though, because this is going to be polyatomic ion, and I want to explain how to do that. So here I have arsenic and 3 oxygens, and overall they have a -3 charge, which means an extra 3 electrons. So here's what it looks like. Arsenic has 5 valence electrons plus, and then each oxygen has 6, which means there's 18 here, plus I got another 3 valence electrons because of this. That means an extra 3 electrons. So 5 plus 18 is 23, plus 3 is 26 electrons. So we have to account for 26 electrons here. And you know what? I didn't actually go back and account for how many do I have? 12. So that would be here between hydrogen. That's 2, 4, 6, 8, 10, 12. 12 electrons, okay? So we are in good shape with that structure for 46A. Now I go back here to 46D, and I'm looking for 26 electrons. So here's what I do. The first thing I do is I try and figure out which one's going to be my central atom. I'm guessing it's going to be AS because AS looks like this with 3 bonds. It has, it looks just like phosphorus or nitrogen because it's in that group. It's got 5 valence electrons, and there's 2 that are paired together, which means they're a lone pair, which means they probably won't bond, although, like, we'll get to that. And then I have single electrons here, which is probably where the oxygens are going to bond. So I'm going to do this in blue. I'm going to erase this so I have more room. So my arsenic is going to be, I'm going to do this like that. Now I'm going to try and fit the oxygens in, and I'm going to fit them in. I'm going to assume, and I almost always assume this, I'm going, unless something happens, I'm going to assume that the single electrons here with arsenic are where we're going to place our oxygens to look like this, like that. So the first thing I'm going to do is make single bonds. I always make single bonds first, like that. And I notice I've got a problem. And my problem is that I have single electrons on each one of my oxygens. Actually, that's not a problem at all because of these 3 electrons that are given to me because of the polyatomic ion charge. So what I do is I simply make pairs. I'm going to put them in red. There's a red electron, there's a red electron, and there's a red electron. And what that means is that each one of my, if we take a look, each one of my central atom has 1, 2, 3, 4, 5, 6, 7, 8 for an octet. Each one of my oxygens, if you count them, including the bonded electrons, has 1, 2, 3, 4, 5, 6, 7, 8. So they all have an octet because all 3 oxygens are the same. So I'm just going to go back to blue, and I always do when I have a polyatomic ion, I always put it in brackets, and then because I put my -3 here to show I have 3 extra electrons, and this is what my my polyatomic ion looks like. Always with the brackets when there's a charge. See what you can do with E and with F, and we'll continue on for this one. Now this one's going to be, write the following molecules or ions for sulfur oxygen, write the single Lewis structure that obeys the octet rule, and calculate the oxidation numbers and formal charges of all atoms. Wow. Okay, so that's going to be a lot. After I do A and B, actually no, I'll do A and C, so you get to see again a molecule and a polyatomic ion, and we'll do the formal charge on all the atoms. So here I got sulfur, oxygen, and oxygen. And then I kind of fit them together as best I can to make them look like, this is not going to be easy. There's going to be some double bonds here. So my sulfur is going to be there. I'm going to make that look like that. And I may do something that looks like this. So I can double bond. Let's see if I can double bond with this oxygen and then double bond with this oxygen. Now oxygen likes a double bond, so that's actually not a bad thing. So that's not a bad thing for oxygen, but sulfur here, if you take a look at sulfur, you'll notice that sulfur has 10 valence electrons now. It has an expanded octet is what we call that. So let's see if this works as far as there's the Lewis structure that obeys the octet rule, except not for, well, if we want to do it for every one of them, what I can do then, I guess, is I can take away a double bond into a single bond and make sure one of the oxygens has this. This would be an octet. This would be for all 3 to have an octet. So I count one on the left hand oxygen, 1, 2, 3, 4 for the lone pairs of electrons, and then I got 4 for the bonds, so that's 8 total. I got the double bond is 4 for sulfur, the lone pair is 2, and the single bond is 2, so that's 8. And then, of course, I have 3 lone pairs for the right-hand oxygen and a bonding pair, so that's 8 also. So that's for the octet like that. Now let's go through and do the formal charge. The formal charge is, remember, it's valence electrons, minus assigned electrons. Okay, assigned electrons are the ones, actually here, I'll do this in this color so you can see this. The assigned electrons are going to be in red. Again, we're going to just assume that that's an appropriate way to abbreviate assigned. And here's what I do to count. So I have the first oxygen, I have the sulfur, and I have the second oxygen. And for valence electrons, for each one of them, it's going to be 6, 6, and 6 because they're in the same group. The periodic table. Now the assigned electrons for the left-hand oxygen is 1, 2, 3, 4, 5, 6 because I break this in half. So that means 6 for that one. This is 1, 2, 3, 4, 5, 6. So I break that in half, and that gives me 6 for that one. And then this one is, no, I screwed that up. This one only gives us 5. Sorry about that. So 1, 2, 3, 4, 5 for that sulfur, and this gives us 1, 2, 3, 4, 5, 6, 7 for that. So that means 0 plus 1 minus 1. Okay, so that's with all of them following the octet rule. Let's go down to letter C. That's what it's asking us to do, so that's what I'm going to do. Let's go down to letter C. I'm going to move this stuff out of the way, so there we go. That wasn't what I want to do. There we go. Move this stuff out of the way, and now let's do SO3. So here I have an S. See, none of this changes. I got an S that looks like this. I got 3 oxygens. One of the oxygens is going to have to like that. Another one's going to have to go like that. And another one's going to have to go like that. So the first thing I'm going to do is I'm going to draw a single bond and a single bond. Notice that I have 2 extra valence electrons. Those 2 extra valence electrons, can I do it? I was close. I got close there. Those 2 extra valence electrons are going to go in the single bonded oxygens. One's going to go there and one's going to go there. So now I have each one of those oxygens has an octet and a single bond to sulfur. My only problem then is up here at the top oxygen. I'm going to erase that and show you what I'm going to do with that. Notice that the top oxygen here, and I'm going to use green to show you this, has 2 single valence electrons, then 2 are paired. So I'm going to make those 2, let's see if I can get this to work. I'm going to get oxygen, 2 pairs, and then the single, and I'm going to put them here so I can double bond this to sulfur. Now this is going to give us an expanded octet for sulfur, but well, maybe instead of a double bond there, maybe I can do this, and then that might give everybody an octet. I'm going to use both a single bond for oxygen there, and then all of oxygen has its 6 electrons, and these 2 come from sulfur. These 2 bonding electrons here and here come from sulfur. Now each one has an octet, so that should work. That's what it asks us to do. The 2 green ones are extra electrons on those 2 oxygens, and it looks like sulfur gave its 2 electrons to bond with oxygen so that oxygen could keep all 6 and just act like it has 6 pairs of lone pairs of electrons. So let's now do the, so if you count them here, each one of my atoms has an octet. Let's do the let's do the assigned now. So this is the valence and assigned electrons. For the first one, now let's see if we can do this correctly here. The first oxygen right here, the second oxygen, and the third oxygen. Okay, so that's 1, 2, 3, and then the sulfur. So I'll do sulfur here, and I have, as far as valence electrons, let me go up so you can see the sulfur. Valence electrons is 6. Assigned electrons is 1, 2, 3, 4, 5. 5. The first oxygen is 6 for valence electrons, and 1, 2, 3, 4, 5, 6, 7. So there's -1, there's a +1. How about oxygen number 2 is 6. 1, 2, 3, 4, 5, 6, 7. 7 -1, and oxygen number 3 is 6 valence electrons, and 1, 2, 3, 4, 5, 6, 7. Okay, so this is a lot of different numbers for the assigned electrons. We have +1, -1, -1, -1. That gives us these two cancel out to give us 0. There's a -1 plus a -1 gives us a -2, which is what the -2 is here. Okay, see what you can do with B and D. And that's it for part 1.